Floods are becoming more frequent. Traditional flood mapping methods use numerical models or machine learning models with Earth observation datasets. However, these approaches face accuracy, scalability, and interpretability limitations. So what if we could improve flood mapping accuracy and also see the model outcomes? In this video tutorial, I will show you how to do this with a unit model and a gradient weighted class activation mapping technique. I'm going to use a dataset downloaded from Kaggle, so you can also download the dataset from this link. Alright, so this video tutorial is organized as follows. First, I'm going to start with the environment setup and library installation. Second, I will move on to pre-processing the datasets. And then third, we'll set up the unit model architecture. And then finally, we are going to run the gradient weighted class activation function so that we can get the heat map visualization. Right, so before we go into the code, first of all, we need to make sure that we change the runtime so that we are connected to the GPU. So make sure you are connected to T4 GPU here. Right, so the first thing that we are going to do is to mount our Google Drive so that we have access to the flood dataset that I downloaded from the Kaggle link. Following that, we are going to import the necessary libraries that we are going to use for the data manipulation and visualization. And next, we are going to set the directory where we are going to access our data. So the data set is in Google Drive, and then in this folder called flood data. Right, after that, we are going to define a function that we are going to use to load and pre-process the images and masks for the unit model. So here we are going to make sure that our images are resized so that they have dimensions 512 by 512, and we are also going to make sure that the data set is normalized so that it is in the range between 0 and 1, so that it can be used in the unit model. So next we are going to sort the images and mask so that they are aligned. So this is important because we want to make sure that each image and its corresponding mask are aligned. Okay, we want to make sure that this they are meshed correctly. Otherwise, we are going to have errors when we run the model. And then we are also going to print these data sets so that we can check the size of the training and test data set. So here for the training, we have 203 images and 203 corresponding masks. And for the test, we have 87 images and 87 corresponding masks. Right, next, we want to visualize a sample image and a corresponding mask so that everything is fine. So if we run this chunk of code, we are going to display the sample image here. The right one here is an image in RGB. As we can see, it is showing the flooded areas, and the sample mask is showing the flooded areas here in white, and the non-flooded areas in black. So next, we are going to set up our unit model So before we do that, I just want to briefly talk about the unit. So what is a unit? So unit is a convolutional neural network architecture, which was originally designed for biomedical image segmentation. However, it has now been used for various computer vision problems. For example, we are now using it for the segmentation of satellite imagery. Right, so the unit consists of two main parts. So we have the encoder, okay, the encoder, this part, the encoder, which is responsible for downsampling the input image, and then we have the decoder part, which is responsible for upsampling the image to the original size. Okay, so more information about this image is found in this paper, right? And I'm also going to leave a link to the detailed guide, which we explain more about the unit model. Right, so for this tutorial, we are going to set up the unit model using the TensorFlow and the Keras libraries for image segmentation. So we are going to have the convolutional layers, the dropout layer, and the max pooling 2D layers, as well as the callbacks, which incorporates the early stopping and model checkpoint. Right, so as I said, the encoder is for the feature extraction, where we have the downsampling happening, and the decoder if for the upsampling, where we have the image restored to its original size. And we are also going here to to use a custom metric, which is the intersection of a union, so that we evaluate the model performance. Right. So first we are going to import our the TensorFlow and Keras libraries, and then we are going to define the IOU metric here function. And then after that, we will define the unit model. So the unit model consists of first the input image. So the input image here, sorry, not the input image, the input, which is going to take an image with the size of 512 by 512 pixels. So this input image has got 3 bands. And then next we have the encoder. So the encoder has got 4 blocks. Okay, so each block contains the 2D conv 2D layer with a ReLU function. So the ReLU is just a nonlinear activation function which allows the network to learn complex patterns in the data. And then we have the dropout. So the dropout is just a layer which is inserted between the convolutional layers, so that we prevent overfitting. So the dropout is just for regularization. And then we have the max pooling 2D. So this max pooling 2D is responsible for downsampling. Right, so this is about the encoder, and the decoder here is got 3 blocks. So the blocks are containing the conv2D transpose, okay, and for upsampling, and then we have the concatenation with the corresponding encoder, And then we also have the dropout and the final convoluted 2D layer. Right, for the output, final output, we have the conv 2D with activation, which is sigmoid, so that we can do the segmentation. Right. Next, we're just going to instantiate the unit model, and as I've said, we have the input image size, which is 512 by 512 pixels, and the images have got 3 bands. And here we are going to use Adam as the optimizer, and we are going to use the binary cross entropy for the loss, and our metrics here, we have got accuracy and the IOU. Right, then we are going to print the model summary, and the model summary is just going to show the model architecture as I've briefly explained before. Right. Next, we are also going to configure the callback function so that we can optimize the unit training. So here we have the early stopping, which is going to stop training if there is no improvement after 10 epochs. And then we have the reduce LR on plateau function, which is going to lower the learning rate by 0.1 if the performance of the model stagnates after 5 epochs. And then finally we have the model checkpoint, which is going to save the best model weights during the model run. Right, so these callbacks function are very important because they help prevent overfitting, and they also are responsible for enhancing training efficiency. Right, we are also going to apply data augmentation. So we are going to use the TensorFlow image data generator function. So this is actually going to artificially expand the training data set. So it uses a number of transformation like rotation, shifting, and flipping, so that we increase the size of training data set, and then we can get better results. So after that, we are going to train the model using the fit method with the augmented data. Here we are also going to define a validation data set which is based on the test set, and we are going to run the models with 100 epochs, and we will define the early stopping and then the learning rate adjustment, and as defined by the callback functions. Right, if we run this chunk of the code, it takes a bit of time because it's running the model for 100 epochs. So you need to be patient until the model finishes running. So after that, we are going to evaluate the model. As I said, we are going to use here the test loss accuracy and IOU as the metrics for validating the model. Remember, here we are using the test data which the model is not seen. Right, we can also plot the figures showing the accuracy and loss. Okay, so the results show that here the test loss is about 0.3, while the test accuracy and test IOU is 88 and 0.88 and 0.75. Okay, and the graph shows that the model is actually doing well. It's not bad. We have a small difference between the training accuracy and the validation accuracy. So we are not really experiencing a problem of overfitting here, which is quite good. So next we are going to save the unit model here, because we are going to use this later when we look at the Grad-CAM. When we are going to set up the Grad-CAM for the explainability part. Right. So after that, we are just going to perform the prediction using the test data set, and here we are also going to display the results. Okay, so here are the results of the model prediction. Here we have the original input image, and then we have the original mask, and then we have the predicted mask. And then we can see here that the model is done some predictions pretty well, and in some areas we have obviously misclassifications, for example in this part. But what is interesting is that in the predicted mask here, it looks like the model has managed to pick up this pattern, but in the true mask the pattern is missing. So that means that also there's an error with our original mask. So this is quite interesting. And then if we look at the second image, we see also that the model is struggling in some parts. For example, here it seems that it is just overestimated. Okay, this part is not non-flooded as seen, and also we can also see some misclassifications here. So this indicates a problem with the model prediction. And if we look at the third image, okay, we can see like really the problem of the underestimation here. So we have some serious misclassification problems in some images. Okay, so next we want now to use the Grad-CAM in order to interpret the decisions of the unit model. Okay, in particular, we will visualize the parts of the input image that influence the unit model prediction. So this approach is very important because it helps us understand where the model is focusing during the segmentation. So first, in order to do that, we want first to check or we want to inspect the model in order to identify the specific layers that we can later use for our Grad-CAM visualization. So if we run this code, we are going to print the layers, and this layers just shows the structure of our unit model, and we will be interested in the convolutional layers, which are going to guide us or show us how the model is performed. Okay, so what are we going to do? So first we will load our libraries, and then next we are going to load unit model that we have saved before. So this is quite important. And then following that, we are now going to define the generate layer Grad-CAM function. Okay, so this is useful in order to extract the feature maps from a specified convolutional layer, and it's also going to use the gradients in order to compute the importance weight for these feature maps. So these weights are the ones that are going to be used to create a heat map, which is later going to be resized, okay, and then color mapped, so that we produce the Grad-CAM heat map, right? And this is going now to highlight the image parts, showing us how the model is performed during the segmentation. Right. So if we run this code chunk, next we are now going to visualize the results. So we are going to display the original images, and then the Grad-CAM heat maps that we have produced, and then we are going to overlay the Grad-CAM heat map on the original image, so that we can try to understand the model outcomes. So first here we are just going to load the images, the test images that we want to visualize. So we have the original test image, A5, and then 1022, and then 3045. Okay, so once we have this, we are also going to take the convolution layer that we want to analyze. So here I've selected this convolution layer, conv 2D11. So this is the one that we are going to check. Right. So where is this coming from? Remember, we printed the convolution layers. So this is the conv 2D_11. So this is the final layer. So we want to visualize this layer, so that it gives us an idea of how the model is performed. So remember, just one thing that I forgot. What are we going to doing here? We are taking the model, and then we are taking the original images, and then the convolutional layer, and then we look at the target class. For example, the flooded or non-flooded class. Okay, so this is what we are basically doing. Right. So if we run this code, we are going to get our results. So here for the first image, so this is the original test image, and this is the Grad-CAM heat map that has been produced, and then this is the overlay of the Grad-CAM over the heat map, or over the original image. Right, as we can see here, we can note that the model seems to be doing very well in dominant flood areas. So these dominant flood areas, they are mapped quite well, okay, according to the model. Okay, so these dominant flood areas with water, they are mapped quite well. But we can see that there may be problems, because some small parts, especially near these high-rise buildings, they are not well captured. So it means the model is struggling capturing these areas. And we can also see, like this area in the upper right part of the image, it's also not clearly mapped here. So the model seems to have missed this. And we can also see on the overlay that areas near the buildings, they appear not being affected by flooding, and also the part that I've mentioned. So again, the model shows here that it's having problem with the classification. And then if we look at the second image, here the misclassifications are apparent. For example, we can see that, for example, this is a building, and it is here highlighted as flooded, as water. But this is a building rooftop, if you can see clearly. So this is clearly a misclassification. This is because this rooftop color is almost similar to this water area. So this is a big problem. Guys, so this gives us an idea that the model is using a color as one of its attributes to do the segmentation. So that is why it did the misclassification. And also, if you can look also here, you can notice that we have another misclassification of this the building here. So again, this is quite important, right? And we can see that again, for the dominant water areas, it seems that the model is doing a good job. But we have this major misclassification. That means we cannot really trust the model. And then finally, in this image again, we can see, like in the dominant water areas, the model seems to be doing a good job, right? But there are other parts of the image that the model also could not clearly distinguish. For example, if we look here on this side, it seems the model is having a hard time to do the prediction. So these are very important insights that shows us how the unit model is performing. So probably we will need to improve, say, the original training dataset, especially the mask. It seems there's a problem with the mask in this case. So this is quite important. Right, so in summary, we have seen that the unit model performance is relatively good if we look at the accuracy metrics. However, the flood maps show that there are some significant misclassifications. We have observed a lot of these areas where the model has underestimated the flooding. And the Grad-CAM visualization also provides us very important insights, showing the areas where the model is focusing on its segmentation on, or its prediction on. So this is quite important. And again, we noted that the color appears to be one of those features, or one of these attributes which is being used for the segmentation. All right, so this tutorial is just an introduction to demonstrate deep learning approach for flood mapping, and also demonstrating the explainable deep learning methods such as the Grad-CAM, so that we can understand how the model is performing. Right, so this approach is quite important because it helps us build trust in the model outputs, and I think it is quite useful for flood disaster management. So please, to learn more, you can download the detailed tutorial guide at Geelabs. So this is a PDF that you can download. And again, I'm also going to leave a Python code on GitHub so that you can try to run it. So thank you very much. See you in the next video.